Have you ever wondered, what really happens when we look deep enough into the past that time itself begins to blur? You see, when the James Webb Space Telescope opened its golden eyes to the universe, we expected beauty, shimmering galaxies, elegant nebulae, the soft glow of cosmic dawn. And, well, we certainly got that. But what we didn't expect was confusion. Webb didn't just show us the universe, it challenged everything we thought we knew about it. Because what Webb saw, out there in the first few 100 million years after the Big Bang, simply shouldn't exist. Galaxies too massive, too structured, too mature, appearing at a time when, by our best calculations, the cosmos should still have been barely awake. Enormous black holes, millions of times the mass of the sun, already fully formed. Light bending, stretching, whispering to us across more than 13 billion years, saying, "You still don't understand me." And that's the thing. Webb's discoveries aren't breaking physics, they're revealing it. They're showing us that the universe is not wrong, just honest. Honest about its complexity. Honest about how little we truly know. As Brian Cox once said, the universe isn't strange, it's just telling the truth. So perhaps the real story isn't about distant galaxies. It's about us. About how every new image from Webb is, in its own quiet way, rewriting our understanding of time, of matter, of beginnings themselves. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. And, I'd love to hear from you. Where are you listening from tonight? It's always fascinating to see who's joining us from all around the world. So let's continue. When the first deep field images from the James Webb Space Telescope appeared on our screens, something inside the world went completely still. It was as if time, paused for a heartbeat, letting us look not only outward but backward, back through 13.5 billion years of cosmic memory. The light Webb captured was ancient, stretched thin by the expanding universe, arriving like a whisper that had traveled longer than any human word ever could. And, that whisper carried more than beauty. It carried contradiction, challenge, and wonder all tangled together. Webb is not just a telescope, it's, a time machine. It peers so far that what it sees no longer exists in the form it shows us. The galaxies in those frames have aged, collided, vanished, and yet their light keeps coming, crossing a cosmos that is still growing, still learning how to be vast. That means every pixel is both memory and evidence. We're not just seeing where things are, we're seeing where everything began learning to become what it is. Well, to understand that, we have to think about redshift, the strange, stretching of light as space itself expands. Imagine light as a sound, a note played on an endless violin string. As the universe grows, that string is pulled tighter, and the note drifts lower, redder, older. The farther away the source, the deeper its tone. And, when Webb looks into that crimson distance, it hears the first chords of creation, the faint hum of matter assembling itself after the Big Bang. So when we say Webb looks back in time, it's not poetry, it's physics. Light takes time to travel, and the farther it journeys, the older it becomes. To see a galaxy 13 billion light-years away is to see it as it was 13 billion years ago. The telescope doesn't move through time. We do, through the act of seeing. It's not out there. It's in here, in our minds, trying to piece together the sequence of cosmic events from the fossils of light. And, That realization changes something subtle in the way we think about observation itself. We are not detached spectators. We are participants in the unfolding of knowledge. Every photon Webb collects ends its ancient journey in our awareness, completing a loop that began when hydrogen first met gravity. That's not just science. That's a conversation across eternity. The first images showed galaxies shaped like fragile shells, spirals, and filaments tangled in golden dust. They shouldn't, by some models, have existed so soon after the dawn of time. But there they were, old souls in a young universe. It's as though the cosmos had hurried its own evolution, sculpting complexity faster than we had predicted. And, that puzzled scientists in the best possible way. Because when the universe surprises us, it isn't failing our theories. It's teaching us humility. We keep learning that each new instrument is both a lens and a mirror. It shows the cosmos, yes, but it also shows our assumptions about it. When Hubble first looked deep into the dark, we thought we'd seen the edge of time. Now, Webb pushes beyond that edge, revealing that our limits were really just temporary comforts. It's not that the universe is stranger now, it's that we are finally seeing it as it is. Not chaotic, not illogical, but honest. Brian Cox once said, "The universe isn't weird, it's just being truthful." And that feels truer than ever. Because the light Webb brings home is truth in its oldest form, raw radiation from moments when space itself was learning how to breathe. We look at those patterns, those tiny smudges of infrared glow, and we see a universe that was already writing its story before we learned to read it. That's what makes it so emotional for scientists. Behind every image is not just data, but time. Time so ancient that it has outlasted stars, planets, and entire galaxies. We're looking at something that has survived billions of years of entropy to reach our eyes. And yet, it arrives, softly, quietly, like dust settling on the lens of consciousness. Well, the first thing many astronomers felt was not triumph, but doubt. Because some of those early galaxies appeared too mature, too massive. According to the LCDM model, structure should build slowly from simplicity to complexity. But Webb was showing a cosmos that seemed to rush its own story. Either our instruments were misleading us, or our understanding was too small. And, the latter feels more likely. You see, every advance in astronomy has carried that moment of shock. The instant we realize nature owes us no consistency with our expectations. When Galileo first turned his lens to the sky, the moons of Jupiter defied his cosmology. When Hubble saw that the universe was expanding, Einstein had to erase his own cosmological constant. And now, with Webb, we're learning again that the cosmos is not built to comfort us. It's built to exist. And, that's a good thing. Because without that discomfort, we would never ask better questions. Science moves not from certainty to certainty, but from wonder to wonder. The unknown is not a gap to be feared. It's a space to be filled with curiosity. We grow older, clocks tick, theories shift, and each generation redraws the map of reality. Think about this. Every photon Webb captures began its journey before Earth existed. Before the Sun, before the Milky Way spiraled into form. That light passed through eras of cosmic violence, through ionized clouds, through voids, through gravitational fields that bent its path, and still found us. It's not just observation, it's inheritance. We are the final stop on an ancient voyage. And, the way that light changes as it travels tells us about the very fabric of space-time. Each stretch, Each shift toward red is a record of the universe's breathing, its expanding lungs of space. The greater the red shift, the younger the universe we see. It's not time travel in fictional sense, it's time translation. We're reading a story written in light. That's why Webb's infrared eyes matter so much. The older the light, the more it's stretched beyond visible color. Where Hubble saw darkness, Webb sees heat. It turns absence into revelation, transforming the black between stars into a tapestry of glowing beginnings. It's not just looking deeper, it's listening closer. And that's how, in the first months after its launch, Webb found galaxies so early that they forced us to reconsider the timeline of cosmic structure. These were not mistakes, they were messages. The universe was telling us, again, that it had always been more efficient, more creative than we imagined. Well, this ability to see the infant universe is not just a technical achievement, it's a philosophical one. For the first time in history, human eyes are seeing their own origin not as myth, but as measurement. That's profound, because it means we are the universe becoming self-aware. It's not that we're observing it from outside, it's that it's observing itself through us. And, when you realize that, the numbers on a screen become something like prayer. Not in a religious sense, but in a sense of awe. Because behind every spectrum line, behind every calculated redshift, there's the echo of creation itself. The Big Bang was not a moment, it was a continuing gesture. And Webb lets us watch that gesture still unfolding. The mirror segments of the telescope gleam like golden leaves unfolded in the cold. Each segment aligned with microscopic precision, catching light that had traveled for eons just to touch it. And those tiny reflections combine into a single image, a single truth about how everything began. It's not just engineering, it's empathy with the universe. So here we are in 2025, living in an age where our machines can see what our ancestors could only dream about. But with that vision comes a responsibility to not mistake clarity for completion. The universe still holds more questions than answers, and that's good. Because questions are how we stay alive to mystery. The light keeps coming. We keep listening. Somewhere in that endless exchange between signal and silence lies the real story of cosmic expansion, a story that will lead us next into a deeper puzzle, where time and space no longer agree on how fast they're growing. That's where we turn next, to the tension that still splits the universe in two. The tension began quietly, almost invisibly, buried in numbers. When astronomers compared two ways of measuring how fast the universe is expanding, the results refused to agree. It seemed small at first, a rounding error perhaps, a statistical whisper easily lost in the noise. But, the more we refined the data, the louder that whisper became, until it turned into something impossible to ignore, the so-called Hubble tension. It's strange. Well, how something as vast as the universe can stumble over something as simple as disagreement between two numbers. One number comes from the cosmic microwave background, the faint afterglow of the Big Bang itself, frozen across the sky like the memory of creation. The other comes from the Cepheid variables, stars whose steady pulsations allow us to measure distances to nearby galaxies. Both should describe the same cosmos. Both should agree on how quickly space stretches, and yet they don't. That's the paradox. If the cosmic microwave background is our baby picture, the Cepheids are our adolescents, and the two versions of us don't match. The early universe predicts an expansion rate of about 67 kilometers per second per megaparsec, while the local measurements, Those closer to home say it's closer to 74. The gap is too wide to be a fluke, too stubborn to fade away. And, the deeper scientists dig, the more this rift feels like a crack in the foundation of cosmology itself. We used to think of the universe as a clean, consistent expansion, one story told in perfect mathematical rhythm. But, Webb's discoveries and the improved local data it supports suggest the story may have more than one tempo. Maybe space isn't stretching evenly. Maybe time itself flows differently in different regions. Or maybe, and this is harder to admit, our equations are missing a verse. Well, cosmologists are not strangers to contradiction. Every great leap in understanding begins with numbers that refuse to obey. Einstein's equations once predicted a static universe. Hubble's observations proved it was expanding. Now, almost a century later, we stand at a similar crossroads. The universe, it seems, is expanding, but not quite the way we thought. It's not that the data is wrong. It's that the cosmos might be more complicated than our models allow. And, that's what makes the Hubble tension so haunting. It's not just about numbers, it's about reality itself. If the two expansion rates are both correct, that means something fundamental about the structure of spacetime has been hiding in plain sight. Maybe the dark energy driving cosmic acceleration isn't constant. Maybe it evolves. Maybe what we call a cosmological constant is anything but constant. That possibility changes everything. Because if dark energy changes with time, then the future of the universe is not fixed. The cosmic expansion could accelerate faster than we expect, tearing galaxies apart sooner. Or it could slow, folding everything back toward a quiet collapse. It's not destiny. It's dynamism. The universe is alive with uncertainty. And, when you think about it, that's not terrifying. It's beautiful. Because uncertainty is where discovery begins. The Hubble tension is not a sign that we've failed to understand the cosmos. It's a sign that the cosmos is still speaking, still evolving, still keeping secrets worth chasing. Brian Cox once said, "This might be the most important problem in modern physics, because it touches the very fabric of space and time." And, well, he's right. It's not just about measuring expansion. It's about questioning what expansion means. Is space stretching uniformly, like dough rising in an oven? Or is it folding unevenly, rippling with unseen forces? When Webb began sending back its deep field images, cosmologists hoped for clues. The telescope's precision could refine the distance ladder, testing whether the Cepheid method was truly accurate. It could also probe galaxies so distant that their light carried an imprint of earlier expansion. If both methods converge, the tension might dissolve. But so far, the opposite has happened. Webb's clarity hasn't erased the discrepancy, it has sharpened it. And, maybe that's exactly what we need. Science advances not when questions end, but when they multiply. The more the data resists explanation, the closer we get to the edges of understanding. The Hubble tension reminds us that simplicity was never the universe's priority. It's not built to please us. It's built to exist. Think about this. If two methods of measuring the same cosmos give two answers, perhaps they are not measuring the same aspect of reality. One looks backward in time to the first photons ever released. The other looks outward into the living present of galaxies. So maybe the universe itself has changed. Maybe what was true for its youth is not true for its maturity. It's not contradiction, it's growth. That, idea might sound radical, but the evidence hints at it. Observations of distant supernovae suggest that the acceleration of cosmic expansion has not been perfectly steady. The data wavers, faintly but persistently, as though dark energy were breathing, pulsing through space-time like a cosmic tide. If that's true, then the Hubble tension is not an error. It's a message, a whisper from the cosmos reminding us that even the void has rhythm. Well, some researchers have proposed that the discrepancy could come from early dark energy, a brief episode shortly after the Big Bang when the universe's expansion sped up more than we expected. That burst could have left subtle fingerprints in the cosmic microwave background, altering the value we infer for today's expansion. It's not a patch. It's a hint of hidden history, a forgotten acceleration buried in the first few 100,000 years. And, others think the answer may lie in the fabric of space itself. Maybe space-time is not perfectly smooth, but slightly lumpy, and our measurements from Earth just happen to sit in a region expanding a little faster than average. In that case, the difference is not cosmic, but local. A statistical accident written into our coordinates. That would be comforting, maybe, but it feels too neat. The universe rarely offers tidy coincidences. Every time we try to flatten its strangeness, it surprises us. So perhaps we should stop searching for a mistake and start listening for a new pattern. Maybe the laws of physics themselves bend differently at cosmic scales, revealing subtleties of gravity we've never glimpsed before. Einstein's equations, after all, were never meant to be final. They were meant to be faithful. Faithful to observation. Faithful to the dance between mass and curvature. And if that dance has changed tempo, well, maybe we just haven't learned the new rhythm yet. And, that's the humility the Hubble tension demands. It asks us to accept that even our most elegant models are sketches drawn in pencil, not ink. The universe can erase and redraw them at will. The real task of cosmology is not to defend old diagrams, but to keep pace with a living, expanding mystery. So when you stand under the night sky and imagine space stretching, don't think of it as a steady balloon inflating evenly. Think of it as a symphony, where each region plays its own tempo, each galaxy its own note. The music sounds unified from afar, but up close, it shivers with variation. And it's within that variation that the truth hides. Maybe that's why the tension feels so human. We too expand unevenly. Our understanding grows in fits and starts. Our knowledge stretches and then stumbles. Our curiosity outpaces our comprehension. It's not just the universe that's inconsistent, it's us. But in that inconsistency lies creativity, the force that keeps discovery alive. The Hubble tension, for all its frustration, reminds us that the cosmos still has boundaries we can push. It's not broken, it's beckoning. Every unanswered question is an invitation to rethink what constant really means. Maybe constancy itself is an illusion born of limited perspective. From the right angle, even permanence might shimmer with change. And, well, as Webb continues its watch, we might one day resolve the discrepancy. Maybe new data will bring harmony to the two expansion rates. Or maybe we'll find that the rift between them is the doorway to a deeper theory, a bridge toward understanding dark energy, or even the true nature of space-time itself. Either way, the tension is not the end of the story. It's the heartbeat between chapters, the cosmic pause before revelation. The universe is not silent. It's just speaking a dialect we haven't yet learned to translate. And so, as Webb peers deeper, beyond galaxies and into the architecture of early matter, we turn our attention to something equally unsettling: the galaxies that shouldn't exist at all, the ancient giants that seem to have aged faster than time allowed. That, is where the next mystery waits, glowing faintly at the edge of everything we thought we knew. When James Webb looked deeper into the cosmic past, it stumbled upon a paradox that felt almost poetic. Galaxies that seemed to have grown old before time itself had the chance to stretch its limbs. It's strange, deeply strange, to think that structures so massive, so mature, could exist just a few 100 million years after the Big Bang. The laws of cosmology said they shouldn't be there. The timeline said they couldn't. And yet, there they were, glowing softly in the darkness, vast, defiant, ancient. That contradiction sent ripples through astronomy. These weren't tiny fragments of matter slowly coalescing. They were giants, galaxies brimming with stars, dust, and complexity far too soon. According to the standard model of cosmology, the LCDM framework, it should have taken billions of years for such order to emerge. Matter needed time to cool, to gather, to form the first small galaxies that would later merge into larger ones. But Webb's early images shattered that script. What we were seeing was not the universe crawling toward complexity, it was racing toward it. And, maybe that's what unsettled scientists most. If these galaxies are truly as old and massive as they seem, then something in our understanding of early cosmic evolution is incomplete. Either the galaxies are not what they appear to be, or the universe learned to organize itself faster than we've ever imagined. It's not that one side is wrong, it's that both may be incomplete. Well, one possible explanation is that these galaxies only look old. Their light, rich and red, could be misleading us. Young stars, especially massive blue ones, burn intensely and fade quickly. Their combined light, seen through the dust of their birth clouds, can mimic the spectral signature of ancient populations. In other words, the galaxies might not be ancient. They might just be bright imposters, dressed in the colors of age. And, that's the delicate thing about cosmic observation. Light is both messenger and trickster. It tells us the truth of what was, but it filters that truth through distance, through dust, through time. A redshift can mean great age, or great distance, or both. And, deciphering which is the art of astronomy itself. Still, the more Webb observed, the harder it became to dismiss the evidence. The galaxies weren't just luminous, they were massive. Their inferred masses suggested the existence of hundreds of billions of stars only a few 100 million years after the Big Bang. That's not a small adjustment to theory. That's a new tempo for cosmic evolution. To grow that fast, the early universe must have been astonishingly efficient at converting gas into stars. But efficiency alone doesn't explain it. The matter had to gather first, and gravity, slow and patient as it is, needs time. Unless, of course, there was help. Dark matter, the invisible framework holding the universe together, might have played a more active role than we thought. Maybe it didn't just guide matter, it hurried it. The invisible scaffolding could have funneled primordial gas into dense knots, accelerating the birth of galaxies long before we expected. So it's not that the universe broke its own rules, it's that we, never fully learned them. We assumed the early cosmos was a slow burn, but Webb shows us a universe eager to ignite. A universe that, in its infancy, was already building the bones of everything to come. And that idea changes more than our equations. It changes the story we tell about cosmic history. We used to imagine the early universe as a kind of soft blur. a fog of hydrogen waiting to be sculpted by time. But now, it seems, structure was there almost immediately. The first stars didn't hesitate. The first galaxies didn't crawl. They leapt into being. Well, there's another layer to this mystery. If galaxies were forming this quickly, then the first black holes must have too. Those black holes would feed on the same collapsing gas that formed the earliest stars, growing hand in hand with their host galaxies. This, hints at a cosmic partnership older than we thought, the bond between galaxy and gravity, between creation and collapse. And, well, when we see these early galaxies, we're not just seeing the first light. We're seeing the first balance between order and chaos, between structure and void. The same forces that tore space apart were already knitting it back together. It's not destruction, it's design. Some scientists have suggested that these galaxies might challenge the LCDM model itself. But, others remind us that discovery doesn't mean destruction, it means refinement. Our models are tools, not commandments. The LCDM framework still explains much of what we see, but perhaps it needs tuning. A new parameter to account for early bursts of star formation or the faster cooling of primordial gas. It's not the end of a theory. It's the next version of one. And, maybe that's the most honest way to see it. Every generation of astronomers inherits a model that fits the sky until it doesn't. Then the sky teaches us again. The early galaxies are not errors in data. They are lessons in humility. The cosmos doesn't bend to our math. We bend to it. Take the Sears 1749 galaxy, for instance, one of the earliest and brightest candidates Webb found. Its light began its journey when the universe was barely 300 million years old. Yet its brightness, its compact shape, and its star content make it look like a mature galaxy, billions of years older. Whether that galaxy truly defies time or simply tricks our instruments, it forces us to confront the edges of certainty. That confrontation is where science lives. We learn not by confirming what we already know, but by failing to fit what we see into what we expect. And each failure is a door, each contradiction a new direction. Well, what Webb has shown us, is that the early universe may have been less empty and more organized than we thought. Perhaps cosmic filaments, the great dark tendrils of matter that connect galaxies even today, were already forming, shaping the path for stars and systems before light could even escape them. The universe wasn't waiting for complexity. It was born with the instructions for it. And, in a way, that feels almost human. We think we grow into understanding, but maybe, like the cosmos, the seed of understanding is there from the very beginning, hidden but ready. The universe didn't learn how to evolve, it simply remembered how. There's a kind of poetry in that. The galaxies Webb sees are fossils of speed and structure, relics of a time when physics was fluent in creation. To look at them is to witness the first choreography of matter, the first architecture of time. They remind us that the story of the universe isn't one of chaos slowly becoming order. It's one of order emerging within chaos, quietly, inevitably, beautifully. And, as more data pours in, the mystery deepens. Each observation sharpens the question, how early is early? If galaxies existed this soon, what came before them? Were there even smaller seeds, proto-galaxies or star clusters, that Webb's mirrors have not yet resolved? The closer we get to the beginning, the less the word beginning makes sense. So perhaps the truth is that there was never a sudden start, just a continuous unfolding. a cosmic breath that never really stopped exhaling. The galaxies we see are just the first ripples of that breath, carrying memory, motion, and meaning across time. And, it's here that the next mystery begins to take shape. Because within those galaxies, buried deep in their glowing hearts, Webb has found something even stranger. Massive black holes, impossibly old, impossibly large, already sitting at the centers of galaxies that should have been infants. How could such monsters have formed so fast? What kind of universe breeds gravity wells that grow faster than stars themselves? That's the question that waits just beyond this chapter, where light gives way to shadow, and creation meets collapse in the first dark hearts of time. When the light from those impossibly ancient galaxies reached us, it carried another enigma hidden within it. Dark cores, monstrous and serene, glowing from the centers of systems that should have been far too young to hold them. The James Webb Space Telescope, with its golden eyes open to the past, revealed not just stars being born, but shadows forming beside them. Supermassive black holes, already millions or even billions of times the mass of our Sun, existing when the universe was still taking its first breaths. It's, unsettling in a way, because these entities shouldn't, by any ordinary cosmic logic, exist so soon. That contradiction strikes at the heart of cosmic chronology. How can something so immense, so gravitationally voracious, arise when there hasn't yet been enough time for matter to fall together? To form a black hole of that size by the conventional route, through the slow collapse of massive stars and the patient accretion of gas, should take billions of years. And yet, Webb's instruments show us these titans already settled into place a few 100 million years after the Big Bang, like ancient kings presiding over a kingdom that had barely been born. Well, one explanation, if it can be called that, is what scientists now call the direct collapse hypothesis. Instead of starting from a single dying star, these black holes may have formed straight from enormous clouds of primordial hydrogen collapsing under their own gravity. No stars, no explosions, just pure infall. Gas rushing inward until gravity defeated radiation, until space itself folded into shadow. And, that process could have produced black holes 100,000 times the mass of the Sun in one leap, seeds ready to grow rapidly through the dense matter of the early universe. But even that still leaves us with questions. Because for such a collapse to happen, the gas must remain cool and stable. It can't fragment into stars first. And that means, the conditions must have been exquisite, almost fine-tuned, with just the right balance of temperature, density, and cosmic radiation. It's not that it's impossible, it's just that it's improbable on a universal scale. And yet, improbabilities, in the grand theater of the cosmos, seem to happen all the time. There's another possibility, and it's even stranger. Maybe some of these black holes were born before stars, before galaxies, before anything we would recognize as structure. Maybe they are primordial, ancient remnants from the very beginning, formed in the first fractions of a second after the Big Bang. In that chaos of expanding plasma, tiny quantum fluctuations could have seeded regions dense enough to collapse directly into black holes. If that's true, then some of the massive cores we see now might be older than galaxies themselves, fossils of the universe's first instability. That idea sounds like science fiction, but it's not. It's mathematics and light, bending toward the same improbable truth. Because, well, when Webb looks into those luminous centers, what it's really seeing are clues to gravity's oldest habits. Black holes are not anomalies, they're inevitabilities. Given enough density, enough time, and enough imbalance, they are what the universe does to itself. And yet, there's still something haunting in how fast they appear to have grown. If these early black holes were born massive, they must have fed even faster, consuming matter at near the theoretical limit. But feeding requires fuel, gas, dust, and debris. And the early cosmos was not exactly abundant in that sense. So, how did they eat? How did they gather enough material to become supermassive in a cosmic heartbeat? That question doesn't just challenge our astrophysics, it challenges our intuition about time. That's the paradox. Maybe fast and slow means something different at cosmic scales. Maybe in those dense early epochs, accretion, the act of swallowing matter, wasn't a gradual process but a flood. The first galaxies, still raw and chaotic, could have funneled enormous streams of gas directly toward their cores. And, in that gravitational feast, the first black holes could have ballooned to monstrous sizes before the universe had even cooled from its birth. We've seen evidence that supports this picture. Webb has found quasars, brilliant beacons powered by black holes, shining from epochs less than 1 billion years after the Big Bang. Their light, bright enough to drown entire galaxies, tells us that those central engines are already millions of solar masses. And it's not just one or two, it's dozens, maybe hundreds. The universe was already alive with them, already forming hierarchies of matter and gravity. It wasn't chaos, it was choreography. Well, if black holes and galaxies co-evolved this early, then we must rethink which came first. We used to believe that galaxies formed stars, and the densest clusters of those stars eventually collapsed into black holes. But, maybe it's the reverse. Maybe black holes were the architects, not the aftermath. The gravitational seeds around which galaxies crystallized. It's not stars gathering to form gravity. It's gravity calling stars into being. That inversion changes everything. Because it means that the relationship between creation and destruction is not linear. It's cyclical. Black holes, the very symbols of collapse, might be the reason anything exists at all. They are not endpoints. They are engines. They shape, organize, and even stabilize their surroundings. Without them, matter would drift forever, structureless, silent. And, that's what Webb's data seems to whisper. The light from those young galaxies is not uniform. It's curved, distorted, brightened in the center by gravitational forces so intense they sculpt the very image we see. Those distortions aren't flaws, they're fingerprints. Each one tells a story of a black hole already writing its signature into space-time, bending light into arcs of memory. It's strange, well, how the darkest objects reveal themselves through brightness. A black hole doesn't emit light, yet everything it touches glows in protest. Gas swirls around it, heating, accelerating, screaming in radiation before falling beyond the horizon. That, contrast, the dance between illumination and disappearance, feels almost symbolic. The cosmos hides its deepest truths not by erasing them, but by wrapping them in light. And that, might explain why humanity keeps staring at these impossible centers. There's something deeply familiar about them, not just in physics, but in feeling. They're places where everything known collapses into silence, and yet from that silence, new understanding emerges. It's not just collapse, it's transformation. The mystery deepens when we realize how organized these early systems appear. The accretion disks swirling around their black holes are already stable, already aligned, as if the universe had practiced this choreography countless times before. It's not a learning process. It's memory. Gravity, remembering how to dance. And, if that's the case, then perhaps black holes are not exceptions to the universe's rules. They are the rules made visible. They show us the limit of matter, the edge of time, the point where physics turns inward to think about itself. To study them is not to look at destruction, but at reflection, the cosmos seeing its own shape in the curvature of gravity. Scientists often say we don't yet need new physics to explain these early giants, only new understanding of old physics. But maybe the distinction is smaller than it sounds. Sometimes, when old truths are rearranged in new light, they become new truths altogether. And Webb's discoveries, every pixel of them, are quietly redrawing our mental maps of the possible. So when we ask how these colossal shadows came to exist so soon, maybe the real question is why we thought they shouldn't. We assumed that creation takes time, that complexity must crawl from simplicity. But the universe keeps showing us otherwise. It leaps, it improvises, it composes faster than our equations allow. It's not rushing, it's remembering. And in that remembering, we find our next horizon. Because within those bright, furious quasars, amid all that gravity and fire, lies another question. What do these black holes do to their galaxies in return? How does their radiation, their magnetic force, their hunger shape the worlds around them? That's the story that follows. How light and shadow coexist, how galaxies live and die by the heartbeat of the darkness within them. In the wake of those early black holes shaping their galaxies, the universe itself began to reveal something almost paradoxical, a kind of quiet order emerging long before there should have been time for order at all. The old models, the ones built from simulations and assumptions of simplicity, used to describe the young cosmos as a fog, chaotic, shapeless, a sea of hydrogen clouds slowly condensing under gravity's patient hand. But Webb has painted a different picture. Instead of a messy beginning, we find filaments, clusters, alignments, patterns written across space, as if the universe, from the very start, knew how to organize itself. That realization changes more than just the tone of our equations. It changes our sense of what beginning even means. If structure appeared this early, if gravity and dark matter were already sketching the cosmic web just a few 100 million years after the Big Bang, then the universe wasn't stumbling toward coherence. It was leaping into it. It's not chaos becoming order. It's order revealing itself inside chaos. And, that's a different kind of creation story altogether. Well, the thing is, every image Webb sends back tells the same story in a different language. You look at one deep field view, and what you see is not randomness but rhythm. Galaxies clustering along invisible threads, the bright knots where matter has fallen into the deep wells of dark matter. These aren't accidents. They're fingerprints of gravity working with precision and purpose. The dark matter, though invisible, has always been the skeleton of the cosmos, and now, through Webb's eyes, we can trace its outline for the first time. And, that's what scientists mean when they talk about the cosmic web. It's not metaphor, it's literal structure. Long, thin strands of dark matter stretch between galaxies, connecting them like veins through which the universe circulates mass and momentum. The bright galaxies that Webb captures are not floating alone in the void. They're glowing nodes in this vast network, beacons where matter condensed most efficiently. The web isn't just scaffolding, it's choreography. This early order suggests that dark matter didn't simply sit by as a silent background player. It may have guided the birth of galaxies with remarkable efficiency. Simulations that once predicted gradual formation now seem too slow, too hesitant. The real universe, the one Webb is revealing, appears to have skipped steps, forming its architecture faster than any model expected. That's both exhilarating and unsettling, because it means our physics, while elegant, might still be missing something essential about how matter moves and clusters when time itself is young. And yet, even in this revelation, there's harmony. The filaments Webb reveals are not arbitrary. They follow the same large-scale structure that astronomers have mapped in the modern universe. What we see billions of years later, the superclusters, the great walls of galaxies, the cosmic voids, all of that is already present, embryonically, in the first billion years. The early universe was not a blank canvas. It was a sketch waiting to be colored in. So maybe we've been underestimating the intelligence of physics itself. Not intelligence in a human sense, but the way the laws of nature conspire toward balance. Gravity gathers, pressure resists, expansion stretches, and somewhere between those forces, symmetry arises. It's not design, it's inevitability. And, Webb's vision lets us witness inevitability unfolding in real time. When scientists processed the first deep-field spectra from Webb, they found more than galaxies. They found filaments of ionized gas connecting them. Those glowing bridges, faint and delicate, are the arteries of the cosmic web itself. They carry the residue of the first elements, hydrogen, helium, a trace of lithium, woven into lines that would one day feed the stars. To see that, is to realize that structure isn't imposed on the universe from the outside. It's born from within it. The cosmos is not something that became organized. It was organizing itself all along. And that, may be the greatest quiet revelation of all. The early universe was not empty space slowly filling with light. It was a framework of potential already humming beneath the surface. Every filament, every cluster, every galaxy to be was already whispered into existence by the invisible hand of gravity. The physics didn't need time to learn. It simply needed light to show what was always there. That also reframes the role of dark matter. For decades, we've thought of it as passive, inert, a background component that only interacts through gravity. But now, seeing how quickly it carved order into the cosmos, we start to wonder if there's more to its story. Maybe dark matter isn't just scaffolding, it's sculptor. Maybe it has properties that subtly influence how baryonic matter behaves, cooling gas faster, guiding flows more efficiently, giving the universe a head start on complexity. Well, none of this diminishes the mystery. If anything, it deepens it. The more organized the early universe appears, the more we must question what drove that organization. Could quantum fluctuations from the Big Bang itself have left imprints that guided matter like invisible blueprints? Or did the fabric of spacetime contain, from the beginning, the memory of structure, a kind of gravitational handwriting etched into its geometry? It's not just physics, it's almost poetry, the way something so vast can act with such quiet coherence. And, when you think about it, that's exactly what Webb is showing us. A universe not of accidents, but of patterns. It's not that randomness vanished. It's that order emerged faster than our minds can follow. The galaxies Webb reveals are not scattered seeds. They're constellations of intention, bound together by forces older than stars. Maybe that's why the images feel almost spiritual. There's a sense that the universe isn't improvising. It's remembering, The filaments, the clusters, the early symmetry. They're echoes of the Big Bang's original rhythm. We grow older, clocks tick, and yet those patterns endure, unchanged, across billions of years. They remind us that chaos is not the opposite of order. It's the raw material from which order blooms. So perhaps the most humbling lesson from Webb's early discoveries is that simplicity was never the starting point. It was an illusion. From the very first second, the cosmos was weaving complexity, layering matter and motion into shapes we are only now learning to read. It's not a story of progress. It's a story of revelation. The structure was always there. We're just now turning on the lights. And, well, if the universe could organize itself this efficiently, what does that say about the role of dark energy? That mysterious force still driving expansion today? Could the same harmony that built the cosmic web be connected to the same subtle balance pushing it apart? Maybe, gravity and dark energy are not enemies, but partners in the same cosmic equation. One gathering, one stretching, both composing the rhythm of existence. That, idea leads naturally to the next question. If the universe knew how to structure itself, could it also have known how to create environments for complexity on smaller scales? Around stars, within planets, inside chemistry itself? The order we see on the largest scales might not end with galaxies. It might continue inward, into the molecular dances that make life possible. The connection between cosmic order and biological order might not be coincidence. It might be continuity. And that's where Webb's gaze turns next, not outward into the cosmic web, but inward, toward the dusty disks surrounding young stars, where chemistry begins to mimic creation. The same forces that organized galaxies now shape atmospheres and molecules. The same symmetry that built filaments in space now whispers in carbon bonds and frozen water. It's not just a story about galaxies anymore. It's about the possibility of life, written in the same universal rhythm that started it all. When Webb turned its gaze from galaxies to the smaller, quieter theaters of creation, the disks of dust and gas where planets are born, it was like shifting from the symphony of the cosmos to the whisper of chemistry. The grand design of the universe, suddenly folded into something intimate. Molecules spinning in the light of young stars, elements combining in unexpected ways, new worlds still half dream and half dust. That change of scale doesn't make the story smaller. It makes it deeper. Because in those disks, circling stars just a few million years old, Webb found something that startled even the most seasoned astronomers. Some of them were missing water. Entire regions of forming planets, once thought to be oceans in waiting, showed not the spectral fingerprints of H2O, but the sharp, silent traces of carbon dioxide and silicates. It was as if the recipe for life had been rewritten in another language. And, that question, where is the water, echoed through labs and observatories alike. For decades, we've assumed that water was the universal solvent, the thread connecting chemistry to biology. It's in our metaphors, in our search for exoplanets, in the way we define habitability. Follow the water, we said. But now, Webb, with its mid-infrared vision, shows us worlds where water isn't the protagonist at all. Instead, carbon compounds dominate, thickening in atmospheres and swirling through dust rings like invisible ink waiting for a spark. Well, this doesn't mean life can't exist there. It means, that our imagination has been too narrow. Perhaps there are chemistries that thrive without oceans, forms of organization that use other solvents, other bonds, other rhythms. It's not just that life could be different. It's that chemistry itself refuses to be ordinary. The data from these protoplanetary disks, especially those around stars like PDS 70 and HD 16296, show an astonishing diversity. Some disks brim with methane and complex hydrocarbons. Others glimmer with carbon dioxide and sulfur dioxide, with barely a trace of water, vapor. And that tells us something fundamental about how planets are built, not just from what's available, but from what survives. The radiation from the young stars, the winds, the temperature gradients, they all sculpt what molecules remain stable. A little too much ultraviolet light, and water is broken apart. A little too little, and the chemistry freezes before it can begin. It's easy to think of these disks as static, but Webb reveals motion, constant recycling. Gas flows inward, dust drifts outward, and in the collisions between tiny grains, new minerals are forged. Silicates melt, carbon chains lengthen, and somewhere in that restless balance, the first molecules of future atmospheres are born. We see the building blocks not as fixed ingredients, but as travelers, moving between heat and cold, between light and shadow. And, the strangest part is how familiar it feels. The same carbon dioxide that chokes our skies on Earth glows in the infrared spectra of newborn worlds. The same methane that flickers in the haze of Titan drifts through alien clouds light years away. It's not that these molecules belong to us, it's that we belong to their story. So when Webb finds a disk poor in water but rich in carbon, we shouldn't see absence, we should see variation. Nature doesn't play by one rule book. It improvises. It composes new melodies from the same elemental notes. Not just hydrogen and oxygen, but sulfur and carbon and nitrogen, weaving in combinations we haven't yet imagined. Well, scientists once thought that without water, complex chemistry would stall. But the spectra tell another tale. In some of these disks, temperatures and pressures create strange liquid phases, supercritical carbon dioxide, molten salts, or ammonia-rich ices that can dissolve organic precursors. It's not Earth's chemistry, but it's chemistry all the same. And, that means the boundary between life and lifelessness might be broader than we ever guessed. This realization forces us to reconsider what we mean by habitable. Maybe it's not about replicating Earth's conditions at all. Maybe habitability isn't a destination, but a range, a spectrum of possibilities where complexity can emerge under any solvent, any sky. The universe might not be searching for Earths. It might be experimenting with every permutation of chemistry it can invent. And that, makes Webb less a telescope and more a translator. Its instruments, MIRI, NIRSpec, don't just collect light. They read molecular language. They tell us when carbon meets oxygen, when silicates absorb heat, when ices shatter and reform. Each spectrum is a story, a flash of methane, a whisper of ammonia, a silence where water should be. And from those stories, we begin to see a truth that's, both unsettling and liberating, that the recipe for worlds is as diverse as the stars themselves. That diversity is the universe's signature. In one system, you find carbon worlds, planets that might have graphite crusts and diamond rains. In another, oxygen worlds, where silicate mountains and vapor seas coexist. It's not that one is right and the other wrong. It's that the cosmos refuses monotony. Even in its chemistry, it resists repetition. And, that brings us to something almost philosophical. We've always measured other planets by their likeness to our own. Too hot, too cold, too dry, too alien. But maybe, well, the point isn't to find another Earth. It's to understand why Earth is one version of many. That, realization doesn't make us smaller. It makes us part of a larger pattern. We grow older. Clocks tick. And still, the universe keeps teaching us humility. Webb's images of disks and clouds show that even the most exotic chemistries follow the same fundamental rules of physics. Bonds form, bonds break. Energy shifts, entropy rises. The beauty is not in the exception, it's in the repetition. And yet, each repetition feels unique because the conditions are never the same twice. Consider this. When water is scarce, carbon takes over. And when carbon dominates, entirely new geologies and atmospheres can emerge. A planet rich in carbon dioxide might have an atmosphere thick as syrup, with temperatures oscillating between extremes. Another might trap heat beneath crystalline clouds, glowing red even in darkness. Webb's data hints at worlds like that, unpredictable, inhospitable, and yet strangely coherent. And, well, this coherence is what fascinates scientists most. It's as if the universe, regardless of ingredients, always finds equilibrium. Whether through silicate cycles or carbon feedbacks, through condensation or erosion, balance always reappears. It's not that chaos vanishes, it's that order insists on returning. Well, maybe that's the thread that ties everything together, the idea that chemistry, like gravity, seeks balance. Whether in the collapse of galaxies or the vapor of a young planet, the laws remain the same. The scale changes, but the song is familiar. It's not out there. It's in here, in every atom that remembers where it came from. So perhaps the true wonder isn't that we find exotic molecules. It's that we recognize them. That methane on another world hums at the same wavelength as methane here. That carbon dioxide, wherever it forms, absorbs light in the same fragile way. The cosmos speaks one chemical language, even if the dialects vary. And, Webb's promise is that this language will only get clearer. Its future observations will reach deeper into the mid-infrared, mapping exoplanet atmospheres, tracing isotopes, revealing how temperature and pressure sculpt reality. Each discovery will tell us, not just what's out there, but how matter itself dreams of becoming alive. And that brings us close, almost painfully close, to the next frontier, the search for signatures of life itself. If chemistry can vary so wildly, then biology, too, might take forms we've never imagined. The absence of water doesn't mean the absence of life. It means the presence of something different, something yet to be understood. That, is where Webb's story begins to blur with our own. Because as we stare into these alien chemistries, we're really seeing reflections of possibility, different ways the universe might have chosen to know itself. And in that reflection lies the question waiting in the next chapter. If planets can form so diversely, if chemistry can invent itself anew, then how many of those worlds might have gone one step further, from molecules to memory, from elements to awareness? When Webb turned its attention from the quiet chemistry of forming worlds to the dark, drifting bodies between the stars, the story of creation widened again. The telescope, began to detect something unexpected. Objects the size of Jupiter, or even larger, wandering alone through interstellar space with no parent star to orbit. They were cold, dim, nearly invisible, except for the faint thermal glow that Webb's instruments could still trace. These were the rogue planets. And, well, they changed how we think about what a planet is supposed to be. That definition used to be simple. Planets orbit stars. Stars provide light, warmth, gravity, a system. But these orphans of the cosmos refused to fit. They moved freely, unanchored, following only their own trajectories through the dark. And the strangest part was how many of them there seemed to be. Webb's infrared eyes, sensitive to even the faintest heat, began revealing dozens, then hundreds, of these nomads scattered between young star clusters. It's not that they're rare, it's that we hadn't been able to see them until now. Well, that discovery forced astronomers to rethink formation itself. How could so many giant planets end up alone? One explanation, is chaos. In the crowded early days of a solar system, when gas giants form and migrate, gravitational encounters can become violent. One wrong resonance, one close pass, and a planet can be thrown out, exiled from its home. The system keeps its balance by losing one of its children. That's the story of ejection, a story of loss written in orbital dynamics. But there's another possibility, and it's even stranger. Maybe some of these worlds weren't thrown out at all. Maybe they were born alone. The same clouds of gas and dust that collapse to form stars could, under the right conditions, collapse just enough to form a planet, but not enough to ignite fusion. It's not a failed star. It's an independent planet, a self-contained sphere of atmosphere and chemistry, drifting through the night between stars. And that, suggests that planetary formation is not just a side effect of starlight. It's a universal process that can happen anywhere. Gravity whispers strongly enough. These rogue planets are laboratories of extremes. Without sunlight, their atmospheres cool into exotic phases. Methane and ammonia clouds settle into layers like frozen oceans suspended in air. Deep within, pressure may forge metallic hydrogen, turning their cores into vast, slow-moving dynamos. Some may even have moons, trapped companions orbiting a darkness that never ends. And, when we think about that, the idea of a moon circling a world without a sun, it's both eerie and beautiful. It reminds us that illumination is not the same as existence. The temperature of these planets can drop to just a few dozen degrees above absolute zero, and yet Webb's instruments can still trace them because of the faint warmth that lingers. Heat left from their birth, slowly leaking into the void. It's not much, but it's enough to tell a story. That heat carries signatures of atmospheric composition, molecules like methane, carbon monoxide, and water vapor. Even in exile, these worlds are chemically alive, whispering spectra into space. And, here's where things get even more surprising. In one star cluster, Webb found pairs of rogue planets, two massive objects drifting through space together, gravitationally bound, orbiting each other in the dark. It's not just single orphans, it's couples, duos moving as one. And that, suggests that even in isolation, gravity seeks companionship. Planets find one another, form fleeting systems, miniature galaxies of two. It's not just matter forming order, it's order insisting on being found. That, discovery blurs yet another line. Because if planets can form alone, can they form moons too? Can they have magnetic fields, storms, or even internal oceans beneath thick atmospheres? The answer, well, seems to be yes. Webb's data hints that some of these bodies are not barren. They're dynamic. They rotate. They radiate. They change. Their chemistry is complex, and, their infrared spectra reveal transitions that suggest layered atmospheres, even weather. We used to think that sunlight was the energy source life required. But if these rogue planets have radioactive cores, or tidal heating from captured moons, or thick insulating clouds that trap warmth, then energy, real, usable energy, might still exist there. So maybe warmth isn't always external. Maybe some worlds carry their own fire inside. It's not just the sun that gives light, it's matter remembering heat. And, when you think of that possibility, it makes the concept of habitability far more flexible. A world adrift, without a star, could still host chemistry in its depths. Subsurface oceans, heated from below, could exist beneath frozen shells. It's not Earth, it's not even sunlight-driven, but it's a system, a quiet, enclosed ecosystem, if one ever arose there. Whether it exists at all is still speculation, but Webb has given us reason to wonder. Well, the beauty of these discoveries lies in how they stretch our definitions. A planet without a star, a system without a sun, life, perhaps, without light. It's not contradiction, it's expansion. The cosmos isn't breaking its own rules, it's showing us we didn't know the rules to begin with. Every rogue planet Webb finds adds a verse to that poem, a verse about resilience and diversity. Some of the rogue planets Webb detects might even be ancient, older than their surrounding stars. They drift through interstellar space like fossils, survivors of systems long gone. And that, gives them a kind of quiet dignity. They carry the memory of their birthplaces in their cores, the isotopes and compositions that tell us what kind of star once shone on them. They're relics, not of destruction, but of change. That's what makes Webb's ability to detect them so revolutionary. These aren't bright objects. They're whispers in infrared. It's as if the telescope can hear what the universe forgot to say out loud. Through that sensitivity, we begin to sense that planets may be as common as dust. Not exceptions. Not leftovers. Essentials. The universe seems to form them as naturally as it forms stars. And, this leads to another revelation. If rogue planets are so common, then maybe most planets spend part of their lives adrift. Maybe ejection isn't tragedy, it's transition. A phase in the evolution of planetary systems. Worlds could form, wander, and eventually be captured again by another star. Gravity doesn't erase, it recycles. So the night sky could be full of unseen wanderers, moving silently between constellations. It's not empty. It's crowded with hidden travelers, with histories that don't depend on light. The more Webb looks, the more it finds evidence that the line between planet and star, between system and solitude, is porous. The cosmos doesn't draw boundaries. It blurs them. That realization shifts something inside us, too. We've always associated belonging with orbit, with being anchored to something larger. But these rogue planets, in their solitary paths, suggest another kind of belonging. The belonging of persistence. They exist without orbit, without center, without illumination, and yet they continue, steady, unbroken. It's not dependence, it's endurance. And, that endurance echoes something deeply human. We too move through our own darkness, carrying warmth from within, guided by memory rather than light. The rogue planets become metaphors not just for astrophysics, but for existence itself. Proof that isolation does not mean absence. It's not loneliness, it's continuity in another form. That, philosophical echo makes their study feel almost intimate. We look for them with instruments of precision, but we find something emotional. A reminder that the universe values both connection and solitude. Not every story needs a sun to shine on it. Some stories are meant to unfold in shadow, and Webb, with its golden mirrors reflecting the faintest heat of these wanderers, has shown us that the universe, even in its emptiest corners, is alive with quiet motion. Planets, systems, stars, dust, all of it part of the same slow choreography. It's not stillness, it's subtlety. So when we ask how planets form, maybe the better question is how they survive. Whether attached or alone, bathed in light or drifting through cold, they all follow the same law. Gravity gives them shape, chemistry gives them color, time gives them history. And, through Webb's eyes, we are beginning to see that survival is the universe's true artistry. And yet, beyond even the rogue planets, Webb's data hints at something larger. Massive networks of young stars being shaped by magnetic fields we barely understand. Fields that might, in ways unseen, guide not only planets but entire regions of space. The same invisible patterns that once built galaxies may still be weaving new stories today. And that, is where our gaze turns next. Toward the invisible forces threading through the cosmos, the magnetic symphony that holds the darkness together. When Webb's mirror turned toward the galaxies that should have been young and wild and full of fire, what it saw instead were places already gone quiet. Beautiful but silent. Vast and still, like a breath held too long. These were the sleeping beauties of the early cosmos, galaxies that seemed to have lived fast and then, somehow fallen into slumber. That shouldn't have been possible. At less than 1 billion years after the Big Bang, the universe itself was still a child. Stars should have been forming everywhere, bursting into light. But Webb found some that had already stopped. Well, the first spectra showed the telltale absence of hydrogen lines, the dimming of ultraviolet signatures that mark new stars. These galaxies weren't empty. They were dormant. Their gas, once cool and dense enough to collapse into stars, had vanished or, been stripped away. And, that raised a haunting question. How does something so young learn to rest? The answer might lie in the violent hearts of these galaxies. Many of them, Webb revealed, hold supermassive black holes far larger than expected for their age. These monsters, feeding on gas at furious rates, release winds and radiation that can heat or blow away the material needed to form new stars. It's not just destruction, it's regulation. The black hole eats, and the galaxy sleeps. That balance is delicate, and yet it seems to have been achieved shockingly early. And, it's not only black holes, too. Blame. Some galaxies simply used up their fuel too quickly. The early universe was dense, its gas clouds thick with raw material. In that pressure, star formation could ignite explosively, millions of suns born in a cosmic heartbeat. But the faster they burn, the sooner they fade. Those galaxies, exhausted, became ghostly shells, glowing faintly in infrared light, resting in the aftermath of their own brilliance. It's strange to think of silence as a form of evidence, but that's exactly what Webb records. The absence of certain lines, the dimming of certain hues, the soft reddening of ancient light. These dead galaxies, as astronomers call them, aren't truly dead. They're waiting for new inflows of gas, for collisions or mergers that might wake them again. Even in their stillness, they hold the potential for rebirth. That, idea, the idea of rest as part of creation, feels almost human. It's not just expansion and chaos, it's also pause and balance. The universe, in its youth, already knew how to breathe in cycles. And Webb, captures those breaths one by one. So, So what could have stopped the flow of cold gas that fuels stars? One theory points to feedback loops. When a burst of star formation happens too quickly, it floods the galaxy with radiation and stellar winds, pushing gas outward and heating what remains. The same stars that give birth to light also, paradoxically, make it harder for new light to form. It's not destruction, it's self-regulation. Not just creation, but restraint. And, there's also the cosmic environment to consider. Galaxies don't evolve in isolation. They live in clusters, bathed in the diffuse plasma of the intergalactic medium. That medium can strip away gas, suffocating smaller galaxies in what astronomers call ram pressure quenching. Webb's infrared eyes have started to see hints of this, subtle gradients in color and temperature that mark where star formation has simply, well, shut down. What's beautiful, though, is that Webb can still see the remnants of their past glory. The dust lanes, the arcs of starlight frozen in time. Even in their sleep, they shimmer faintly with the memory of creation. It's not absence, it's aftermath. That, leads to another fascinating puzzle. Some of these sleeping beauties show unusually high metallicity. That is, they contain heavy elements forged in earlier generations of stars. That means they lived intensely before quieting. Their starbursts must have been so efficient that within a few 100 million years, they enriched themselves to levels similar to modern galaxies. It's as if evolution in the cosmos doesn't always move slowly. Sometimes it rushes forward, burns bright, and then steps back into shadow. Well, this challenges one of our simplest intuitions about cosmic time, that youth must mean chaos, and age must mean calm. Webb's findings blur that boundary. The early universe was not a reckless teenager. It was, in some corners, already mature. That, realization forces us to rethink what early means. Maybe time in the cosmos is not linear in the way we feel it. Maybe it folds and accelerates, making room for exceptions, places where gravity, density, and chemistry align just so, and evolution skips ahead. And, well, what does this say about our models? The standard picture, where galaxies slowly grow through mergers and accretion, can't easily explain such rapid formation and quenching. So astronomers are revisiting the role of environment, of dark matter, of feedback, of cosmic web filaments channeling gas. It's not just one mechanism, it's an orchestra. And Webb, quietly, is letting us hear the faintest notes. The most poetic part of all this is that some of these sleeping galaxies might not stay asleep. Over cosmic timescales, gravity will pull them into new interactions, collisions that reheat gas, reignite star formation, and light them up once again. They may die and live again, over and over, through the ages. Not just endings, but intervals. Not just decay, but renewal. The term sleeping beauty fits perfectly, because these galaxies are not gone. They're dreaming. Their light, stretched across billions of years, carries both memory and promise. The universe doesn't mourn their silence. It holds it, waiting for the next crescendo. And, perhaps this too is part of a larger truth. Webb keeps revealing that the cosmos isn't simply expanding outward in chaos, but breathing, pausing, resetting. Every collapse, every lull, every silence is preparation for the next creation. The same balance that forms stars also knows when to rest. It's not the universe winding down. It's the universe learning rhythm. So when we look at these quiet galaxies, we might not be seeing the end of something, but a new kind of order emerging. a subtle equilibrium between energy and exhaustion, between light and shadow. They're not failures of physics, they're reflections of harmony on a cosmic scale. Well, and as Webb continues to observe, patterns emerge between these sleeping systems and the magnetic fields threading through intergalactic space. The fields seem to trace the same geometry, as if the calm and the current are linked. That, connection, though invisible, could explain how galaxies evolve in synchrony across unimaginable distances. And that's where Webb's next revelations lead, to the hidden architecture of those magnetic threads, the quiet forces shaping everything from stars to entire clusters. From the sleeping beauties of the early universe, we drift, toward the grand, unseen networks that hold the cosmos together, toward the magnetic symphony still unfolding in the dark. When Webb began tracing the faintest filaments of light connecting galaxies, the pattern that emerged looked almost alive. What had once seemed like empty space between galaxies now shimmered faintly with structure, with threads of matter stretching across cosmic distances, forming a web so vast it could only be described as a skeleton of the universe itself. And, running through these filaments, invisible yet unmistakable, were magnetic fields, ancient, tangled, and quietly powerful. That discovery was unexpected. For a long time, astronomers assumed magnetism was a byproduct of stars and galaxies, something local, something small. But Webb's infrared sensitivity, when combined with radio data, began to reveal polarization patterns, subtle alignments in dust and plasma that could only exist if magnetic fields were already there, woven into the fabric of space long before the first stars lit up. It's not just that magnetism exists, it's that it has always been there, shaping everything silently. The strange things that we still don't fully understand where these fields come from. Some theories suggest they were born during the earliest instance of the Big Bang, as quantum fluctuations stretched across the inflating universe. Others think they might have emerged later, when the first galaxies rotated and stirred the plasma into currents. But the evidence Webb provides, those faint traces of alignment in the intergalactic medium, points to something older, deeper, fields that predate light itself. Well, that realization changes how we imagine structure forming. We used to think gravity alone sculpted the universe, matter attracting matter, dark matter guiding the dance. But now, it seems magnetism might have whispered instructions too, guiding how gas flowed, how stars clustered, how galaxies spun. It's not just a gravitational story, it's an electromagnetic one. And, when we see those filaments, vast strands of gas, dust, and dark matter threading the void, it's hard not to think of them as veins, not metaphorically, but physically. Energy moves through them. Charged particles spiral along them. They carry not blood, but current. The cosmos conducts itself. The fields bend around clusters, twist near black holes, and stretch across megaparsecs with quiet authority. That quiet power might explain why galaxies align along invisible axes, why their spins echo one another across billions of light years. It's not coincidence, it's coherence. A magnetic coherence written into the universe before life ever wondered about it. And Webb, is helping us see the edges of that hidden geometry. It's strange, isn't it? How something we can't see can organize everything we do see. These fields don't glow or shimmer. They reveal themselves through how dust aligns, how light polarizes, how jets curve from distant quasars. It's like trying to read wind in a forest, not by watching the air, but by watching the sway of the trees. And Webb, with its precision, captures that sway. So maybe magnetism isn't just a force, it's memory. The universe remembering its earliest motion. The stretching of space, the spin of plasma, the slow settling of order out of chaos, all leaving behind a residue, a field that holds the story. It's not out there, it's in here, encoded in every atom, every alignment, every faint tug that keeps the cosmos coherent. And, if you trace these lines far enough, you start to see how galaxies aren't separate islands. They're nodes in a single, immense circuit. The cosmic web isn't static, it hums. Current flows from cluster to cluster, charging the intergalactic medium, driving shock waves that heat gas and spark new bursts of star formation. The more Webb observes, the more dynamic that vast structure becomes. The universe isn't expanding into emptiness, it's expanding into connection. Well, that connection has implications we're only beginning to grasp. Magnetic fields can control how cosmic rays move, how gas cools, even how planets form in distant disks. They may influence the birth of stars by channeling matter into narrow streams, or by resisting collapse just enough to delay it. It's not just one field, it's an orchestra of them, each one playing in harmony with gravity. And, Webb's infrared vision gives us the score. This discovery also stirs something philosophical. Because if magnetism weaves through all of space, then everything, every atom, every galaxy, every human, exists inside a single, invisible network. We're not outside of it. We're inside the current. We live inside the field that once guided galaxies. The same physics that shaped stars also whispers through the iron in our blood. It's not just a metaphor, it's literally true. That, thought changes the tone of everything. It means that the universe isn't just vast, it's continuous. The same lines that connect galaxy clusters connect us too. We're not observers of a distant order. We're part of the circuitry. And, when Webb's instruments pick up the faint polarization of light billions of years old, they're not just mapping space, they're tracing the echo of the same forces that still hum through us now. So maybe that's why the cosmic web feels strangely familiar when we see it. It mirrors the neural networks in our own brains, the branching of rivers, the structure of roots beneath the soil. The patterns repeat across scales not because of coincidence, but because physics likes efficiency. Because nature, whether in neurons or galaxies, finds the same paths of least resistance. That symmetry isn't illusion, it's inheritance. Well, and Webb's continuing survey of these magnetic filaments is beginning to show that they're not uniform. They twist and pulse. They strengthen near dense regions and fade in the void. Some even seem to reconnect, magnetic lines snapping and reforming, releasing bursts of energy that might seed radiation or even trigger matter to condense. It's as though the universe breathes electricity in slow motion. The more we learn, the more it feels like magnetism could be the missing link between scales, between the quantum and the cosmic, between the particle and the planet, between chaos and pattern. Gravity pulls, yes, but magnetism organizes. It draws the invisible map that everything else follows, and Webb, quietly, is drawing that map in light we can finally see. That, light tells us that the universe is not random, not disordered, not mechanical in the cold sense we once thought. It's structured, but softly, held together by threads too fine to touch, but too essential to ignore. Those threads don't just exist, they interact. They vibrate, they sing, and when we translate their harmonics into image and data, we start to hear something that feels almost like intention. And, well, as Webb continues to study these filaments, it also finds how they link back to the galaxies themselves, how magnetic feedback loops might connect to black holes, to jets, to starbirth. The small and the large are not separate. They're reflections. The universe, builds coherence from its own turbulence. So maybe, as we reach deeper into this magnetic web, we're not uncovering something new. We're remembering something ancient. The same order that shaped the first stars still shapes us. The same fields that guided matter then guide thought now. And that, thought carries us forward to the final question. Webb leaves hanging in the starlight. If the universe is so deeply connected, if magnetism and gravity and time all weave into one grand field, then what happens when our understanding itself becomes part of that fabric? And somewhere beyond the filaments, beyond even Webb's golden gaze, waits that next horizon, the limit where science meets the edge of knowing, where the universe, quietly, begins to look back. When we speak of limits, it's easy to think of walls, barriers that stop progress, lines drawn where knowledge fades into mystery. But with Webb, those limits don't feel like endings. They feel like edges of a great map still being drawn, edges that shimmer with light older than any word we have for it. It's not that understanding stops, it's that it changes shape, expanding the moment it meets the unknown. And, that's what the telescope has done again and again. Push our understanding until it breaks open and becomes something new. Well, as Webb's mirror gathers light from billions of years ago, we find ourselves face to face with paradox. The more clearly we see, the more the universe defies simple explanation. Galaxies too massive too soon, stars too organized too early, black holes too ancient to fit the models we trust. It's not that the physics is wrong, it's that it's incomplete. The story of the cosmos keeps unfolding faster than the equations that try to describe it. There's a humbling beauty in that. We build theories like scaffolds, believing they'll hold up the sky. And then Webb points a mirror into the deep and shows us where the structure bends, where the symmetry cracks, where the unexpected light still leaks through. It's not failure. It's invitation. The universe is inviting us to look again, to imagine differently, to rewrite what we thought was certain. That process of reaching, of revising, isn't new. Every time humanity has looked deeper, it has found contradiction first and clarity later. We once believed Earth was the center of everything. Then the sun. Then the galaxy. Then the observable universe. Now, with Webb's images spread before us, we realize there may not be a center at all. It's not that we keep moving outward, it's that we keep letting go. And, when we let go of certainty, something profound happens. We begin to see ourselves as part of what we're studying. The light Webb collects isn't foreign, it's ancestral. Every photon it captures has traveled across time to remind us that we belong to that same unfolding. It's not out there, it's in here, within us, within our atoms forged in stars that Webb now photographs in their infancy. Brian Cox once said that science isn't about certainty, it's about embracing doubt. Webb's discoveries, the ones that confuse us most, are acts of generosity. They show us how vast our ignorance still is, how much room there is left to grow. The telescope doesn't just reflect light, it reflects humility. The deeper it looks, the more it teaches us to kneel before complexity instead of pretending to master it. Well, and there's something human, almost tender, about that realization. Every data set, every infrared image is an offering, not of answers, but of wonder. The universe doesn't mock our limits. It reveals them gently, layer by layer, as if to say, you're not wrong, you're just not done yet. That, awareness changes the way we see progress. Science is not a ladder, it's a spiral. We circle back, refining, rethinking, rediscovering. Webb's findings don't overthrow what we knew. They illuminate the spaces in between, the gaps where imagination must step in. And imagination, is where science and poetry meet. The equations give us structure, but wonder gives us direction. So perhaps the true limit isn't what we can't see. It's what we forget to feel. The night sky, as Webb shows it, isn't a cold void, but a living archive. Every speck of light carries a memory of creation, and every question we ask becomes part of that record. When we reach the edge of what's measurable, the next step is not retreat. It's reflection. The universe expands, yes, but so does our capacity for awe. And, well, maybe that's the quiet revelation behind all of Webb's discoveries, that we're not outside observers of a cosmic play. We are participants, written into the script, made of the same dust that glows in its spotlight. Our curiosity is not separate from the universe's unfolding. It is the universe becoming conscious of itself. That's what Brian Cox meant when he said, we're part of the process the universe uses to understand itself. The telescope isn't just a machine built by human hands. It's the cosmos extending its own senses through us. When Webb gazes back toward the beginning of time, it's not looking at something else. It's looking at its own origin through our eyes. And that thought, that the universe is self-aware in this subtle, indirect way, turns knowledge into kinship. It means that learning isn't about control, it's about communion. Every discovery Webb makes connects us more deeply, not just to the stars, but to the story they tell. We grow older, clocks tick, galaxies drift farther apart, and yet, somehow, understanding keeps drawing us closer. Well, perhaps that's the paradox of progress. The more distant the light, the nearer it feels. When we map galaxies 13 billion years away, what we're really tracing is our own origin story, written in hydrogen, helium, and time. The universe, doesn't resist being known. It just asks that we approach it with patience. And, if there is a limit, maybe it's not physical. Maybe it's emotional. The boundary of comprehension is where mystery turns into meaning, where data becomes reflection, where light becomes memory. Webb's greatest discovery might not be out there in a distant galaxy, but in here, in the way it changes the way we see ourselves. That, is the quiet revolution, the shift from seeking answers to embracing questions. The telescope doesn't promise resolution, it offers perspective. It tells us that the unknown is not an obstacle, but a landscape, a place to wander, to listen, to wonder. So as we stand at the edge of what Webb can see, in this moment of 2025, the journey feels both infinite and intimate. The cosmos stretches on, unending, yet the more we explore it, the more it feels like home. The golden mirrors reflect not just starlight, but the faces of those who dared to look. And, as the last photons from the beginning of time reach our detectors, we realize the story isn't about endings or answers. It's about continuation, the ongoing dialogue between what is known and what still waits in shadow. Beyond the horizon of Webb's vision lies something we can't yet name, but we will. Because curiosity, like light, never truly stops. It just travels onward, seeking another mirror to call its own. In the end, as the golden mirrors of Webb keep gathering the oldest light in existence, what we are really seeing is not the edge of the universe, but the edge of our understanding. Each observation, each quiet pixel of ancient fire, pushes against the boundaries of what we think is possible. It's not that the universe is hiding from us, it's that it's still unfolding, and we are unfolding with it. We don't conquer the unknown. We learn to live beside it, to listen when it whispers back in wavelengths we can finally hear. Well, that's the quiet truth hidden inside all the data and the noise. That discovery is not a war against darkness, but a conversation with it. The cosmos, in its vast indifference, becomes strangely intimate once we realize we are part of its story. It's not out there, it's in here, within every atom of us, within every question that drives us to look up again. The telescope isn't revealing a foreign place. It's holding up a mirror, showing us the face of curiosity itself. Everything Webb has found, the galaxies too old, the stars too young, the planets too strange, isn't contradiction, it's invitation. The universe isn't resisting comprehension, it's deepening it. Every answer births another question, and every mystery widens the horizon of awe. That, cycle is endless, not because knowledge fails, but because wonder never does. So when Brian Cox says we are part of the process the universe uses to understand itself, it's not poetry. It's physics written in consciousness. Webb's mirrors don't just collect ancient light, they collect meaning. They remind us that knowing and being are not separate acts. The more we understand the universe, the more the universe understands itself through us. And, well, maybe that's what the cosmos has been trying to tell us all along. That we are not intruders in its vastness, but its continuation. That we don't study it from a distance. We bloom from it, made of the same carbon that burns in its stars, the same hydrogen that drifts through its voids. The light Webb sees isn't only the past of galaxies, it's the ancestry of thought. Every time the telescope turns its gaze toward something farther, it also turns inward toward the beginning of awareness. It's not just mapping the universe, it's charting the evolution of wonder itself. From the first spark of curiosity to the most delicate equation, we've always been, in some quiet way, part of the universe learning its own name. That, realization doesn't close the story. It opens it. Because if Webb has taught us anything, it's that endings don't exist, only thresholds. Every discovery is a doorway, every mystery a mirror. The cosmos expands, and so do we, endlessly reflecting, endlessly reaching, endlessly becoming. And perhaps, well, in the silence between galaxies, in the long hum of background radiation, there is something like a voice, not in words, but in resonance, saying that understanding was never the destination. It was the journey itself, the slow awakening of a universe that has, at last, begun to recognize its own reflection in the fragile eyes of those who dare to look back.